Okay, in this video we're going to talk a little more about representing position and different ways in which we can view the position of a particle or an object. So let's start by defining what we mean by positive or negative position. Remember, we have an origin and an axis that we give a name, in this case is x. And so if the position of the particle, if the particle is to the right of the origin by convention, we're going to say that is a positive position. If it is to the left, we are going to say that is a negative position. There's nothing in the physics of the object that is positive or negative. That's a convention that we are making. So this is positive and this is negative. Now, the position, the motion that we are studying could be a horizontal or a vertical motion. This is a vertical motion here. And so we have here an origin. We have a vertical axis. We give it a different name just to remember that it's a vertical axis. And if the particle is up above the origin, then we say it has a positive position. If it is below the origin, we say we have a negative position. It would be positive and this would be negative. So let's look at another way to represent position. Here we have a table and we have times here in minutes and we have the position in some coordinate system of an object. So how can we use this table to represent the position, or how can we visualize this position? Well, we can do what is called a position versus time graph, where we have the time in this axis and the position in this axis. So let's see how would that look like. So here we have the time in minutes. So 2 minutes, 4 minutes, 6 minutes, and so on. And here we have the position in meters, 200 meters, 400 meters, 600 meters. And we can see that these represent points on that table that we had before. Another possible visualization is this one here. This is called a motion diagram. And so in this case, we just have the position be plotted at different intervals. This would be like a movie, movie, and these are frames. And so, and you can see here, the nice thing of this visualization is that you can see the velocity vector. We're going to use this a lot because it has a few nice mathematical properties. So let's say we have a position versus time graph like this one here. And so can we get, what information can we get out of that graph? So we can get from position, we can get the velocity. How do we get that? Well, the velocity is going to be related in this graph to how steep the inclination of this curve here. This line here is going faster than this, and this one is going the fastest. So how do we get that inclination? Well, we're going to define it as, we're going to find this this rise here, and then we have this run here, right? This is delta t equals 3 minutes. This rise is 300 minutes. And then we take here the rise over the run, and we take 300 over 3 minutes, and that'll give you 100 meters per minute. So that is your velocity. So the steeper the graph, the faster you're going. This is also called the slope of the graph, and we can use both in when we talk about velocity. So now that we can get the velocity from the position, can we plot the velocity as a velocity versus time graph? And we can, and the way it would look like is this. So in here, we have a velocity that is this. In this section, we have a velocity that is this. And in this section, we would have a velocity that is this. That is your velocity versus time graph. So if you know the velocity versus time graph, can you get the position? You can get that. And so here we have an object. So let's say you're given this graph. So you have an object that is moving at 1 meter per second. And let's suppose that it starts at the origin. So then if it moves at 1 meter per second over 15 seconds, then it'll be 15 meters when it gets there. And then it's moving with a negative velocity of 3 meters per second. So then it'll come back in 5 seconds to the original place. So you can see that we have reconstructed from this graph, we have reconstructed the position versus time graph. So one particular type of motion that we are going to be studying is a uniform motion. Uniform motion is one in which the velocities don't change. So the position versus time graph is going to be a straight line like this one here. So you can see that the slope is the same everywhere, or the rise divided by the run is always the same. This delta x over delta t is always going to give you the same number no matter where you are in the graph. This is called uniform motion, constant velocity motion. So let's see if we can derive some equations for this motion. So we know that the velocity is the rise divided by the run, right? And so what is a rise? A rise is basically the displacement. And the run is just the time interval. So then we can write this as xf minus xi divided by delta t. And so, and this is equal to what? Well, this is equal to the velocity in the x direction. So now I can take xf minus xi, and that is equal to, I can take this number and multiply it and send it to the other side, multiplying. So I'm going to get Vx times delta t. And if I send this to the other side of the equal sign, then I finish with this equation here. And this is the equation for the position versus time of a uniform motion. In here, the acceleration is equal to 0. Another way to write that is delta x is equal to Vx times delta t. One very important concept is that of instantaneous velocity. So if the velocity changes over time, then you need to have a way to tell what the velocity is at a particular time. If you were to calculate the velocity at this time, it would be different than the velocity at this time. The car is going slower in this region than in this, right? So we define what is called the instantaneous velocity. Instantaneous velocity is the velocity that you measure at a particular point in time. For instance, that will be the velocity that you see in your car when you're driving and you see the speedometer. So let's look at how to find that. The way to find that is that we take the graph and we zoom, right? We zoom in a region, right? So we get this region here, and then we do the same. We take the rise divided by the run, and that is your velocity. But that is the velocity at that particular small area. And you can zoom again here, and then zoom again, and then you can get a very, very, very good approximation of the velocity at that particular point by zooming many times. So this is the definition of instantaneous velocity, and this is what we are going to be using a lot, or this is going to be our definition of velocity in the remaining of the class. When we talk about velocity, we are going to be talking about instantaneous velocity. So if you were to find the instantaneous velocity, you have to zoom very small and then do rise divided by run, which is 3 meters divided by 0.2 seconds in this case, and that gives you 50 meters per second. So that'll be the instantaneous velocity at 4 seconds. And that'll be different from the instantaneous velocity at 6, and the instantaneous velocity at 8, or the instantaneous velocity at 2. Each one has a different value because it's changing over time. Another way to see that is that at each point here, the graph has a tangent, And the instantaneous velocity is the slope of that tangent that touches the graph there. If you have a velocity versus time graph like this one here, right, and you want to find the position, you need to find this area. The area underneath this graph is going to be used to find the position, and we'll see a lot more on how to use this in some of the example problems. Okay, so let's stop here, and in the next video we'll talk about acceleration.